In this video, we're going to talk about improper integrals. Now, improper integrals are not integrals that don't know how to behave in social situations. Improper means that the functions that you're integrating, you're looking at either a horizontal or a vertical asymptote in some way. So we'll talk about what that means in just a second. Okay, so let's look at a specific example of an improper integral. This will be our first example. For background, we're going to be looking at f of x equals 1 over, and our goal here is to look at definite integral from 0 to 1 of 1 over x dx. Now, if I look at the graph of y equals 1 over x, what I see is that as I approach x equals 0 from the positive direction, that this curve is approaching positive infinity. So it's a fact that the limit as x approaches 0 on the right of 1 over x is equal to positive infinity. However, that does not mean that this integral doesn't exist. It's possible that this area that I'm shading right here from x equals 0 to x equals 1, it's possible that this area is still finite. So that's a key idea that people often struggle with, which is we want to say, even if an expression involves infinity, that even if a function value approaches infinity, it's still possible for a related expression to be finite. And we like finite things. We like finite things because the things that we experience in the real world are finite. The numbers might be very, very large, but you have $100 bill. You don't have an infinite dollar bill. You might have a $1,000 bill. You might have $10 billion, but there's still a finite amount of money, even if it's very large. So when we make predictions about the physical world, we want to know that those predictions are going to be finite. And one way to think about this is through the metaphor of paint. So if you think about how much paint it would take, or how much ink it would take to cover all of this area, question is, can we buy enough paint that in theory we could cover it if we had forever, or cover as much as we wanted to of it? Or is it the case that if we're doomed to paint forever, that no matter how long we paint, at some point we're going to run out of paint? No matter how much paint we buy, at some point we're going to run out of paint. So that's a metaphor that's helpful sometimes to people in thinking about the area under the curve as a certain amount of paint that they would need to buy, and the curve as or a curve or a part of the x-axis is how much time they have to paint it. Just a rough idea that might work. There's actually a process to determine this number if it exists. The first thing we're going to do is identify that there's a trouble spot. Now, in this example, the trouble spot is at x equals 0, because that's where the vertical asymptote of this curve is. So the second thing we're going to do is create a variable for that trouble spot. So instead of looking at the integral from 0 to 1, instead, I'm going to look at the integral from t to 1. So this is kind of steps 1 and the start of step 2 combined. I'm looking at the definite integral from t to 1 of 1 over x dx. Now, I can use the fundamental theorem of calculus for this, because when I create that t, I'm using it to express some value in here that's between 0 and 1 and that doesn't actually touch 0. So t is strictly between 0 and 1. Because of that, I can use the FTC, the fundamental theorem of calculus here. My antiderivative of 1 over x, be careful, the antiderivative of 1 over x is natural log of x. And then I plug in the bounds and evaluate, so I get natural log of 1 minus natural log of t, minus natural log of t. So I'm going to be looking here at this being natural log of 1 minus natural log of t. This is the expression that I wanted to find. And now I'm going to take this expression and I'm going to go from 2 to 3. I'm going to take the limit as t approaches 0 from the right of ln of 1 is actually equal to 0. So this is just going to be negative natural log of t. Now, natural log of 0 is undefined and it approaches negative infinity. So this actually becomes negative infinity which would just be positive infinity. So in this case, we could say that this area is equal to infinity, or we could say it doesn't exist because it doesn't take on a finite value. And when we say that a quantity exists, we're meaning it exists in the physical sense, like I could have this many apples or this many gallons of paint. So our conclusion is that the definite integral from 0 to 1 of 1 over x dx is equal to positive infinity, or you might also see that this diverges. That's another terminology that's used just like it's used for sums. So let's look at f of x equals 1 over x cubed. And again, it's true that the limit as x approaches 0 from the positive side of 1 over x cubed is equal to infinity. But that doesn't necessarily mean that this integral, it's possible that this integral of integral from 0 to 1 of 1 over x cubed dx could still be finite. So we're going to follow our process here. And as I'm doing this, I'm realizing I made a mistake in the previous example. It's not true that the limit as x approaches 0 of this 1 over x is positive infinity. It's true that the limit as x approaches 0 from the right-hand side is 1 over positive infinity. And I need to also make this limit as t approaches 0 be to the right-hand side, because I'm only caring about values that are strictly larger than 0. So I'm sorry about that mistake. It's a minor fix in notation. It's actually an important conceptual thing. And I'm going to be more careful about it here. So I'm saying the limit as x approaches 0 from the positive side of 1 over x cubed is infinity, and taking the definite integral from 0 to 1 of 1 over x cubed could still be finite. So let's follow our process. Our trouble spot here is at 0. So we're going to be looking for trouble spot at 0. So we're going to replace 0 with a variable, usually t for trouble. So we're going to have the definite integral from t to 1 of 1 over x cubed dx. And here, I'm assuming that t is strictly greater than 0 and less than or equal to 1. So I can use the fundamental theorem of calculus. So my antiderivative of x to the negative 3 is negative 1 over 2 x to the negative 2, or negative 1 over 2x squared. I'm going to take this and plug in the bound, so this becomes negative 1 over 2 times 1 squared minus negative 1 over 2 times t squared. So this is my final expression, and here's the process I use to determine this. The final step in my three-step process is I'm going to take the limit as t approaches the trouble spot. So here's the limit as t approaches 0 from the right of, let's rewrite this so it's in a different order. So let's rewrite this minus, plus, and minus, and switch places. So let's rewrite this as 1 over 2t squared minus 1 over 2 times 1 squared is 1/2. And so calculating this boils down to evaluating this integral. And again, because I'm plugging in 0 here, that doesn't exist. So this is an infinite amount of area. And I feel like we could have seen that geometrically if we looked at the curves that we're involved with here. Now let's look at another example of a curve. Let's look at 1 over square root of x. So if you look at the green curve, it's clear in just the part that we're able to see that the green curve has less area than the red curve. So I'm comparing this 1 over square root of x to 1 over x in terms of their areas from 0 to 1. And I am seeing that it looks like 1 over square root of x has less area. So there's a possibility that maybe this area isn't infinite. And let's compare. It's definitely true that as x approaches 0 from the positive side, the limit as x approaches 0 from the positive side is infinity of 1 over square root of x. But again, that doesn't necessarily mean that this integral is infinite. It's possible, even if you have an infinite process like adding up area, still have a finite amount of area. And that's what we're going to investigate. So first, let's find our trouble spot. So our trouble spot is at x equals 0. And so let's substitute around that and create the definite integral from t to 1 of 1 over square root of x dx. Now this is the same thing as the definite integral from t to 1 of x raised to the negative 1/2 power. And so when I do this using the fundamental theorem of calculus, my antiderivative of x to the negative 1/2 is 1 over 1 plus negative 1/2 times x to the negative 1/2 plus 1. So this antiderivative becomes 2x to the 1/2, and I plug in my bounds. I get 2 times 1 to the 1/2 minus 2 times t to the 1/2. So the second step is to get an expression involving this t, which represents a number that's going to tend towards my trouble spot, but isn't actually equal to. Final thing I want to do then is take this expression and plug it in. So I'm going to take the limit as t approaches 0 on the right, 2 times 1 raised to the 1/2 minus 2 times t raised to the 1. And this I can actually evaluate because I'm just being asked here for the square root of 0. So this is 2 minus 0, which is 2. So shocker, even though this is a curve that tends towards infinity as x approaches 0, it has a finite amount of area. So you can actually shade this, and you could take the amount of paint that it would take to paint a rectangle of area 2. And if you had a bucket with 2 gallons with that much paint in it, you would never run out of paint. You would still be able to paint this entire thing and never run out. Whereas if you looked at 1 over x, no matter how big your bucket of paint was, you would still never have enough. If you had 10 gallons of paint, that's not enough. If you had 100 gallons of paint, that's not enough. No actual quantity of paint would suffice to cover this region.